Thanks.
Right. So yeah, first of all, thank you so much for giving me the opportunity to talk about this work that I've done in collaboration with Laurent Friedel, Susanne Schander, and Mark Schiffer. Part of what I'm gonna talk about was exposed in this paper that we submitted to the archive on September. And because most of us are outsiders to the field, we really value your opinions on the subject, but hopefully the conversation will be interesting too, both ways. And the title is Non-Perturbative S-Matrix Renormalization. So I wanted to begin by sort of motivating why okay, so the general idea first is that we wrote an FRG flow equation for a functional in QFT that generates S-matrix elements directly. All right? So I wanted to start by motivating why we would like to have such a functional by saying a few words about how we usually compute S-matrix elements on a non-perturbative way. And the general recipe is something that looks like what I have in here. So here we have the main steps. The first step is that I compute some functional, big F, as function of field little f. This is already a non-trivial step because it basically amounts to computing a path integral or solving something like the Polchinski or Wetterich equation. Then we compute the endpoint functions that this functional defines, which is basically just taking a bunch of derivatives, functional derivatives. In the next step, I need to solve the so-called quantum equations of motion associated to my functional f. So this is some equation that looks like this, and I'm basically looking for some field configurations f star that satisfy this equation. And in the final step, I need to write my S-matrix elements as functions of my correlators. Okay? So something that I want to communicate in this slide is that these two steps are some sources of inefficiency. So in particular, it might be the case that my quantum equations of motion are non-trivial. And well, it might also be the case that this functional dependence of the S-matrix elements in the correlators is non-trivial. So let me show you two basic examples of this sort of inefficiency in these two steps. So suppose that the functional that I focus on is the partition function, z of j. Well, then my endpoint functions are just correlation functions. Then the quantum equation of motion is just setting my source to 0. So in this case, this is just trivial. And then the way I go to S-matrix elements from my correlation functions is by using the LSE formula. So even though the LSE formula is not too bad, I still have this extra step. If I instead work using the effective action, then my correlation functions are one particle irreducible diagrams. Then I have a quantum equation of motion that looks like this. This is some sort of quantum analog of Hamilton's principle. And this in principle can be non-trivial, especially if I want to deal with curved spacetimes or fluctuating spacetimes. And in this case, even though this case can be non-trivial, this last step is trivial because my functional dependence is just given by the identity function. Okay, so wouldn't it be nice if we find some sort of functional that makes both of these steps trivial or even non-existent? And this is kind of like the motivation to have an S-matrix functional. But let me also say that the motivation goes beyond just practicality, which is what I've explained so far. If we work more closely to the S-matrix, so if we really sort of remove these steps, then we might get some deep conceptual insights into QFT. For example, unitarity is usually framed in terms of the S-matrix. So if we deal with, this project, as I told you, is about renormalizing this S-matrix functional. So working more directly with the S-matrix might allow us to better understand the link between unitarity and RG constraints. Similarly, we might be able to understand more deeply the connection between the freedom in choosing a renormalization scheme and the freedom of under field definitions. And similarly, there's been some general interest in on-shell renormalization. And because the S-matrix is a fully on-shell object, if we learn how to renormalize something closer to the S-matrix, we might also get some insights on this front. So this was our motivation. And in a sense, what I've been trying to motivate is that our driving question was, can we encode scattering information efficiently? Or framed a bit more sharply, is there an S-matrix functional? And in most of my talk today, I'm going to tell you that yes, there are S-matrix functionals. And in particular, the protagonist of today will be a functional S that I've denoted here. So let me explain the notation. This functional depends on both a boundary field beta. So this is some field configuration that lives in the boundary of my spacetime. You can think of it as boundary conditions. And it also depends on a bulk field var phi. And the main point is that this generates S-matrix elements, both if I think of this as a boundary functional or if I think of this as a bulk functional. Namely, when I take derivatives with respect to the boundary functional, then I can generate S-matrix elements. And if I take derivatives with respect to the bulk functional, then I also generate S-matrix elements. And I will, in both cases, avoid this step because I will be directly generating my S-matrix elements. When I take the boundary perspective, I actually don't need to take this step. And I will elaborate on this later. But this is a fully on-shell perspective. And when I take the bulk perspective, then I do have some off-shell field that I need to take on-shell. But my on-shell condition is actually trivial. So it's similar to what happened here with the partition function. Particularly the paper that I mentioned discussed only this branch, and it is for this bulk S-matrix functional that we derived an FRG flow equation. So this will be the larger part of my talk, the second part of my talk, but I wanted to tell you a bit more about the boundary perspective, precisely because it's very interesting that this is a fully on-shell point of view. So that's the general idea. And I wanted to first also clarify what exactly I mean by what is exactly our functional S. Okay, so the definition is written in this expression. It comes in two main factors. One of them, which is written here, is just the exponential of I times the free action of my bulk field. So this K is the kinetic operator, and in particular is the physical kinetic operator. So the mass that appears in here is the pole mass. And this other factor is the partition function that I wrote here, defined as integrating with fields that have some boundary condition beta. So I apologize for the notation. This might suggest that this is some temperature, but let me just emphasize again, this is a boundary field configuration. And then I have a source, J, that I evaluate in this way. So it's K times my bulk field var phi. So the boundary dependence appears as the boundary conditions in this path integral, in this action, as the boundary conditions in this path integral, and the bulk field dependence appears in here and in here. So as I mentioned, whenever this functional depends on both a boundary field and a bulk field, and I can take either functional derivatives with respect to the boundary field or with respect to the bulk field, and both of these perspectives generate S-matrix elements. So now I will, in this first part of my talk, I'm going to talk about the boundary perspective. So what exactly do I mean by saying that my functional generates S-matrix elements? What I mean is this big equation that I have in here, which might at first look intimidating, but it's really just like simple standard QFT manipulations. The basic idea is that, well, on the left-hand side, I have some S-matrix element with incoming momenta P and outgoing momenta K. And on the right-hand side, the most important part is this factor that I have in here. So here I have some superscript notation that indicates that I take, in the first entry, this means that I take n plus n functional derivatives with respect to my boundary field beta, and 0 functional derivatives with respect to my bulk field var phi. So this is what I'm doing in here. I'm also evaluating this functional in some particular var phi, which is any field satisfying my classical and free equations of motion. So the kinetic operator acting on var phi equals 0. This means that, in a sense, this functional in here doesn't really depend on var phi. And this can be seen as follows. Here, I'm writing in my slides as a reminder what the definition of our functional is. And also, by the way, as a notational note, I have some slides that have these glasses, which means that I'm trying to communicate like a key aspect of the talk in this slide. So it's important to focus on that particular slide. But okay, so here I remind you of the definition of the functional. You see that if I evaluate on a field that satisfies this equation, then this first factor is just 1. And then I'm just evaluating at a source j equals 0, which means that what I really have is a path integral, the usual path integral, in which I integrate over fields with boundary conditions beta. So really, the dependence on var phi is quite artificial from this boundary point of view. Okay, so that was this evaluation here. Because I took n plus n derivatives with respect to the boundary field, then this actually depends on points in my boundary x and y. And then I just evaluate this derivative with a particular boundary condition beta equals 0. Then I basically contract this derivative with a bunch of Fourier modes. So these U's are just one particle modes with momenta pi and ki. Depending on my incoming momenta, or depending on whether it's incoming or outgoing momenta, then I will have a complex conjugate or not. And you see that this contraction happens by integrating over the boundary points. Okay, so this is the sense in which I'm generating S-matrix elements. I have some sort of Taylor expansion. I have a derivative, and then I have some field evaluation. I have the contraction, and then my derivatives are evaluated at beta equals 0. So now that I explained what exactly I mean by generating S-matrix elements, I want to tell you why this equation is true. So this is what we want to prove. So the next slide is probably the most technical of my talk. I want to give you I'm of course still skipping a bunch of details that are very interesting, but I just want to give you the gist of why this is true. But in preparation for that slide, I wanted to tell you like a roadmap of the derivation. I will start from this definition of the S-matrix, in which I'm generating some momentum quanta at asymptotic early times, and then I compute the overlap with some momenta that I generate at asymptotic late times. So this is going to be the starting point. Then I'm going to express this creation and annihilation operators using the Klein-Gordon inner product, which will allow me to rewrite this creation and annihilation operators in terms of my quantum field. Then in the second step, I will go from these Q numbers to C numbers using the path integral. And in the last step, I just rewrite these Klein-Gordon inner products that I had now inside the path integral in terms of boundary functional derivatives. So this is how these boundary derivatives will appear. Okay, so now let me show you the crude derivation of this result. Once more, whenever we take the boundary perspective, this is how our functional looks like. This is what we want to prove, and this is our starting point. So in the first step, let me argue the first equality by going from the bottom line to this top line. You see that basically I just replaced any annihilation, all of these annihilation operators by a difference of annihilation operators with the same momentum, just that one of them is evaluated at asymptotic late times, so this is the original one, and one is evaluated at asymptotic early times. And I did something similar for the creation operators, but now this extra part that I inserted is evaluated at asymptotic late times. So in principle, it might seem that this equality shouldn't hold because I added a bunch of terms. When I expand these products, it seems like I added a bunch of terms. But you see that here I added also some time ordering operator, which as an effect, so it does the following. These annihilation operators that I introduced, I evaluated are at minus infinity, so I can move them all the way to the right to act on my vacuum. So basically, on these factors, I just added a bunch of zeros. And similarly, with these creation operators, now they will act on the bra of the vacuum. And I also have a bunch of zeros that I just added. So this equality indeed holds, and you might recognize this as a key step in the usual derivation of the LSE formula. Now, for this second step, I just remember that my creation and annihilation operators are the overlap of my quantum field with the positive and negative frequency modes with respect to the Klein-Gordon inner product, which means that I can rewrite all of these annihilation and creation operators as this Klein-Gordon inner product. And I can also rewrite this time ordering by plugging the Klein-Gordon inner, or plugging my expression into the path integral. So this is the second equality expression that I have here. You see that I basically substituted these first products of differences of annihilation operators as a product of differences of Klein-Gordon inner products. One is evaluated at a time slice which is asymptotically late, and one asymptotically early. And then I have a similar thing for the creation operators, just using now U bars. All right, so then we can use the fact that then we can set the boundary conditions beta to 0, because this is what I actually have in this equation right here. And I can use the definition of the Klein-Gordon inner product. So each of these, you see that will look like this, where V is my mode. But you see that if I set my boundary conditions to 0, then when I do this boundary integral, then this first term will vanish. So I just recover a bunch of modes multiplied by some time derivative of my field. So then here I basically rewrote the same expression, but now I have integrals over the boundary of my spacetime instead of difference of integrals at asymptotic early and asymptotic late times. So if you look at this expression, and this initial expression that and this expression, which is what we wanted to, in the equality we wanted to prove, you see that I have these integrals over my boundary of my modes. I have these integrals over my boundary of my modes. So these expressions only differ by the fact that here I have the derivatives of my functional, and here I have a bunch of time derivatives of my field. So if I can show that inside the path integral, these products of time derivatives equals these derivatives of my functional, then I've actually proven this equality. And one can indeed show that inside the path integral, whenever I take these variations right here, then the only part that contributes, and let me again emphasize, inside the path integral, is the variation of the boundary action. So because I am considering the Dirichlet boundary conditions in my path integral, I need to supplement my action with a boundary term. And if I then compute the variation of this, I will indeed recover this equality, which is the only step that was missing to prove our main identity in here. So hopefully I managed to convince you that indeed we have some our functional, when understood as a functional of my boundary field, generates S-matrix elements in this way. And this you can see as a fully on-shell point of view, because I didn't really need to implement any sort of quantum equation of motion. So I really completely avoid this awkward step that I mentioned in the motivation slide. So I will come back to the boundary functional, which is an object that we would like to renormalize eventually. And part of our motivation to develop the bulk perspective was to somehow use this bulk perspective to be able to renormalize our boundary functional. But for the moment, I will just pause the boundary discussion and go to the main part of our work, which had to do with the bulk perspective. So once again, let me explain you what exactly I mean by generating S-matrix elements from the bulk perspective. So now I have a very similar equation to the one we had before. But now you just see that in my superscript, what I'm indicating is that I take 0 derivatives with respect to my bulk field, with respect to my boundary field, but I take m plus n derivatives with respect to my bulk field. So now the contraction with free modes will be implemented by integrating over bulk points. But now I need to, the dependence on my bulk field is non-trivial. And in contrast, actually, I can basically take any boundary condition in this expression. In particular, for this equality to hold, I not only need to take derivatives, but I need to take my field to be a field that satisfies this on-shell condition. So this means that I need to satisfy the classical free equations of motion implemented with some boundary condition beta. But as I told you, this boundary condition is actually not relevant. I can take any of them. Okay, so you see that this equation really, it's something very simple. It's my free classical equation, which means that even though I do have this extra step of going on shell, in this case, it's rather trivial. So now I'm gonna argue for this equality just as I did before. And the basic idea is, okay, so we want to prove this. The basic idea is that I will argue that whenever I have this contraction with the Fourier modes, this guy equals the kinetic operator acting on my correlation functions. So basically, this would be the right-hand side of the LSE formula. And this is how I will argue for the equality with the S-matrix elements. So let me sort of show you the simplest cases. Let's say that we only take one derivative in here. Well, you can see from our definition that if I do that and apply the Leibniz rule and the chain rule, then I recover an expression of this form. So something like this. And then if I go on shell of my very simple equations of motion, this prefactor is just 1. And then this term vanishes. So what I recover is k acting on this 1-point function. This is a 1-point function because it's a derivative of my partition function evaluated at source 0. So you can begin to see why this looks like what I have in the LSE formula. It turns out that maybe this one derivative case is a bit too simple to explain the general mechanism. So I also wanted to show you what happens if I take two derivatives. So if I do that once more, I apply the Leibniz rule, chain rule, I go on shell. Then what I recover actually is something like this. So now see, once again, I have something like what appears in the LSE formula, but I also have this extra term that might look annoying at first. But remember that this I'm supposed to plug in this contraction with my Fourier modes, which means that this K will act on these Fourier modes, which are on shell, on the, and this is, here I mean the mass shell. And because this was a physical kinetic operator, then basically this guy contracted with my modes gives me a 0. So the only part that is relevant is the one that would appear in the LSE formula. And what can it show that in general, this contraction of my Fourier modes with my functional derivatives indeed recovers the right-hand side of the LSE formula. So this is why this formula holds. So now that I've argued for this, let me go deeper into what we did in the paper. One thing is that this is a particularly efficient way to encode scattering information, but in principle, using this functional, we can do any of the standard calculations that we do in QFT. Just as whenever we work, say, with the partition function or the effective action, we can also recover scattering information. So in principle, like the point of view that we take is that different functionals serve different purposes. If I want to compute correlation functions, or say something like critical exponents, maybe working in terms of Z or the Schwinger functional is the right thing to do. If I want to compute something like running off couplings, perhaps using the effective action is the right thing to do. All of these functionals are equivalent. So we have this diagram that expresses some connection between the functional S, the partition function C, and the effective action gamma. So they all encode the same information. It's just that some can express some physical quantities more directly than others. And we've been emphasizing scattering information. So to give you a gist of how this would be done, so, let me show you how, say, a two-point function can be written as a connected two-point function can be written in terms of S. So for that, let me use this functional t, which is the log of z, the log of S, basically. If you go to our definition of what S means, then you can see that this t looks like this. So I have basically the free field action minus my Schwinger functional. And from this, I can, of course, solve for the Schwinger functional, and then I can take two derivatives, which is what will give me my two-point function, my connected two-point function. And of course, I can invert this. Well, this is what this is really doing, is giving me the two-point function in terms of t, and I can exponentiate to get my two-point function in terms of s. And similarly, I could say I could get something like the 2.1 pi irreducible diagram by using an expression like this one, which is standard in literature. Okay, so there's really a dictionary using all of these functionals. We are just saying that this functional in particular is efficient when we want to think in terms of the S matrix. Okay, so now we took this bulk functional and we derived an FRG flow equation for it. In our derivation, actually this t, this is also why I wanted to introduce this t. This t was very crucial because it's actually easier to derive first an FRG equation for t. The reason for this is this equality that I just flashed before, which is actually structurally similar to a Legendre transform. This means that t is very closely related to the effective action. You see from this expression that if k phi is j, well, if k phi was j, then this would look like some sort of Legendre transform in which I have something like a field times j minus w of j. And we can exploit this structural similarity with the effective action to basically mimic step by step the standard derivation of the Wetterich equation. So that's what we did. That's what we did. Let me just remind you of the usual steps to derive this equation. First, we need to Vig rotate. So now we have a Vig rotated functional S. And you see that for simplicity, now I suppressed the subindex beta, because as I told you, the boundary condition that we choose is irrelevant from this bulk point of view. Then I have a Vig rotated partition function and also some Vig rotated t. Then we have a regulator, which basically means that we substitute all of our kinetic operators by a regulator kinetic operator that has an extra mass term that is momentum dependent. It depends on the scale k. And this is supposed to implement an IR regulator and also my right boundary conditions under my RG flow over k. By introducing this regulator, I'm effectively also regulating t or s. And then we just take momentum at the momentum derivative, which is what appears in the Wetterich equation, to obtain a two-point function, and then just mimic the steps to derive a Polchinski-like equation that I will discuss in the next slides. And in the end, we just re-express everything in terms of S. Okay, so this is just a reminder of what the standard derivation looks like. We just really use this structural similarity to mimic exactly all of these steps. So by doing that, we arrive at this, which is our main result. This is our star equation for our bulk S matrix functional. So let me, well, in case you prefer diagrams, here's a diagrammatic representation of this equation. Here, the dotted line is the free propagator, and we have this operator insertion, which is just the flow of our regulator. So you see that we also get some one-loop equation. And I wanted to point out some things that we see as virtues of this equation. First, this is polynomial. So you see that I don't need to invert any functional operator. In particular, this is polynomial in this Hessian right here. as I've been pointing out, the on-shell equation that we are to implement to compute this matrix elements is trivial, and this is an equation for our functional that efficiently packs scattering information. So to further emphasize what we see this, why we see these things as virtues, we wanted to compare with other FRG equations. So in particular, let's see what happens with the standard Wetterich equation. So this is an equation for the effective action. That means that what I will be generating in the end are one particularly reducible diagrams. And in terms of complexity, you see that this equation requires me to invert this shifted Hessian in here. And it also requires me to eventually solve my quantum equations of motion, which can in principle be highly non-trivial. And this is particularly true if I work on curved or dynamical spacetimes. Also, if I want to care about particular types of boundary conditions. There's also the Polchinski equation in FRG literature. This is for my Schwinger functional W. It generates connected diagrams. And well, this actually has some structural, some complexity similar to this equation. It's polynomial as well. And it also has some trivial quantum equation of motion. I just need to set my argument to 0. And indeed, if you compare this equation to the equation that I wrote here, they basically look the same. It's just that in this case, what we're generating are S-matrix elements, whereas in this case, what I generate are connected diagrams. Okay, so yeah, indeed, this is what I've been saying. Let me just say a few more things about our quantum equation of motion. This is a quantum equation of motion, but it's really just the classical free equations of motion. And note that in particular, setting var phi to 0 satisfies this equation. So this is similar to what happens with the Wetterich equation. Something funny about this equation. So yeah, as if this wasn't sort of like a simple equation enough, there's a way to make it even simpler. And this is by noticing that here, what I have is the flow of my functional. And on the right-hand side, I also have this extra term that also depends on the functional itself. So this is begging for some sort of exponentiation. And indeed, if I use the right exponentiation, we can basically make this second term disappear. The basic idea is that we renormalize our functional by rescaling it with this exponential in here, where F is my regulated free field free energy. So you have trace of log of my kinetic operator. By doing that, we recover this even simpler equation, which now has this nice diagrammatic representation. Okay, so those are these two were our main results. These are our flow equations for the S-matrix generating functional. And this was from the bulk point of view. And as I told you, it would be nice to have an FRG perspective which is fully on-shell. So we wanted to somehow hinge on these equations that we derived to see if we could apply them to the boundary perspective. And so far, we have not been able to do that. But I wanted to tell you some of the challenges that we have faced. So the first thing that we have tried is, okay, this is our bulk equation. Can we, by taking it on shell, somehow rewrite it as a boundary flow equation? So this is basically the question that we have explored so far in terms of this boundary flow equation. This, by the way, allows me to justify my slightly awkward notation in which I have a functional that depends on two fields, because it is when I have this notation that we might be able to exploit this sort of direction. So let me see what happens if I take this equation on shell. First of all, this term becomes a fully on-shell object. So this is a nice feature, because as far as this term is concerned, then I do have something that is fully expressible in terms of my boundary functional. The actual problematic term is this one right here. Because these functional derivatives here we're taking with respect to a bulk field. So in principle, whenever I take these variations and then evaluate them on an on-shell configuration, I can have some directions that are off-shell. So in principle, this derivative here, this Hessian, knows about the off-shell information of my theory. However, this off-shell information is actually, it's almost irrelevant because this Hessian is appearing inside a trace. So you see, because this appears inside a trace, if I take this trace in momentum space, what I'm basically doing is I'm contracting this Hessian with some Fourier modes. But as I argued, the contraction of these sort of endpoint functions with Fourier modes are just S-matrix elements, which I could then in principle re-express as derivatives with respect to the boundary field. But the subtlety here arises in the fact that this trace is over off-shell momenta. So I cannot actually use the equality that connects this guy to the S-matrix elements. So this is sort of like the challenge. Here I sort of like try to say a challenge and then why it's almost not a challenge, but then we have an extra challenge. And we are sort of exploring how to pass this barrier by perhaps considering a particular class of regulators that somehow solve this issue with the mass shell. Or another direction that we have discussed is whether we should change the notion of on-shellness so that it's dependent on the scale k. But yeah, so far this is a very open direction. So yeah, basically the open question that we still have and would be very nice to discuss is whether we can use FRG techniques more directly on the boundary functional. So that takes me to basically conclude. I've been trying to argue today that there are functionals in QFT that very efficiently pack scattering information, namely that they generate S-matrix directly. The most efficient of the ones that I discussed today is a boundary functional. It has a boundary field as in its argument, and this is a fully on-shell object. Then I try to focus more on the bulk perspective because there's also a bulk S-matrix functional, which is off-shell in principle, but it has a very simple quantum equation of motion. And it is for this bulk functional that we derived renormalization group equation, functional renormalization group equation. And so far, it seems that this flow equation has a very simple structure, and we hope that it can be exploited for efficient non-perturbative calculations, scattering calculations. So more of an outlook, I also wanted to say a few words. So yeah, I already asked sort of the main question that we would like to address in the future and perhaps discuss today, which is whether it's possible to find a flow equation for the boundary S-matrix functional. We have some hope that somehow we can use our bulk equation to lead us on the right direction, but so far this has faced some challenges. Another nice thing to do is, I mentioned in the motivation, which is that if we work close to the S-matrix, it will be, because the S-matrix is a fully on-shell object, this might offer us some opportunity to understand renormalization from an on-shell point of view. Then, of course, the challenge is that at some point in the FRG derivation, the very first step was to Vig rotate. But if we really want to deal with scattering amplitudes, we should deal with real time. So we are very sympathetic to this line of research in which the FRG techniques have been tried to be extended to Lorentz signature. Then, we are hopeful that this perspective can be used to enhance our understanding of the connection between RG and unitarity. And this is connected to this recent work in here, in which it was argued that RG conditions and unitarity conditions are very tightly connected. And of course, because the S matrix, the unitary conditions are nicely formulated in terms of the S matrix, understanding how to renormalize the S matrix might help to make progress in this direction. So similarly, I told you that it would be interesting if the S matrix can be used to understand the link between renormalization freedom, meaning the fact that I can, say, choose different regulators in my FRG scheme, and the freedom that we have associated to filter definitions. And the reason we hope that this might be doable is stemming from the fact that the S matrix is actually, has been shown to be filter definition invariant. So somehow renormalizing the S matrix might shed some light in this direction. And very open questions that we are eager to explore are, okay, so eventually if we want to use our equation, we will probably need to come up with truncation schemes. But so far, we don't have any intuition as to what S-matrix truncation schemes look like. So this is a very open question. And of course, the right way to explore it first would be to actually test our equation in some simple examples, which is something that we're really looking forward to do. So that's really everything that I wanted to say, and I'll be very glad to now, well, open the room for discussion.
Thank you very much, Jose. And yeah,